Hello everyone. Welcome to the session on Compton effect. The scattering of photon by electron is called as Compton effect, and it is one of the chief mechanisms by which photons interact with matter. Now, the significance of Compton effect is that it supports the quantum theory of radiation. And it was Arthur H. Compton in 1920s who discovered that when X-rays interact with the electrons of materials like graphite, they get scattered. And the X-rays transfer their energy partly to the electrons so that the electrons acquire a momentum and move in a different direction. So the whole process is considered as a particle collision event between photons and electrons, which has resulted in a change of frequency or wavelength due to the loss of energy of the incident X-rays. Now, let's analyze the whole process mathematically and derive an expression for the change of frequency or wavelength. Now, this figure shows the geometry of Compton scattering. As you can see, the incident photon is interacting with an electron at rest, and it is getting scattered at an angle phi. The electron is also scattered at an angle theta to the original direction. Now, suppose that the photon has an incident frequency nu and the momentum P is given by E by C, so it is h nu by C. The scattered photon is at a different frequency nu dash, so the energy E equals h nu dash and P equals h nu dash by C. The electrons are initially at rest, so the momentum is 0 and it has got a rest mass energy E equals m0 c squared. When it has scattered, it acquires a momentum P, and therefore the final energy E is equal to root of m0 squared c raised to 4 plus p squared c squared. Now we can write the equations for energy conservation and momentum conservation to derive the equation for change in wavelength, which is also called as the Compton shift. Okay, so beginning with the conservation energy for equation for conservation energy. So the loss in photon energy corresponds to the gain in kinetic energy of the electrons. So that can be expressed as h nu minus h nu dash, which is equal to the kinetic energy of the electrons. Okay, now coming to the momentum equation, momentum is a vector, so we need to consider the direction. Okay, so here you can see the photons are scattered at an angle phi with respect to the original direction. Okay, so we can resolve this momentum vector into two directions, that is the original direction and the perpendicular direction. So the magnitude of momentum after scattering, it is h nu dash by c. So the horizontal component is h nu dash by c cos phi, and the perpendicular direction would be h nu dash by c sin phi. Now regarding the electrons are scattered at an angle theta with respect to the original direction. So hence it can be resolved as P, the magnitude of momentum is P, so it's P cos theta, and here it is P sin theta. Now we can write the equations for conservation of momentum. So in the horizontal direction, that is the original direction, the initial momentum of the photon is h nu by c plus the momentum of the electron is 0 because it's at rest initially. So which is equal to, in the original direction, the final momentum is h nu dash by c cos phi, plus for the electron it is p cos theta. Now for the perpendicular direction, initially there is no momentum in that direction, so I can write it as 0, which is equal to, finally the momentum for the photons in the perpendicular direction, it is h nu dash by c into sine phi minus p sine theta, which is the momentum component in the perpendicular direction for the electron. Okay, so now let me call the first equation as equation 1. This is equation 2 and this is equation 3 for the perpendicular direction. Now equation 2 and 3 could be rearranged, and on squaring and adding these two equations, we would arrive at an expression for p squared c squared. That is, p squared c squared equals h squared nu squared plus h squared nu dash squared minus 2h squared nu dash cos phi. This is equation number 4. Right. Now coming to the total energy of the particle. Total energy of the particle can be written in terms of kinetic energy as E equals kinetic energy plus the rest mass energy. Also, there is another equation for total energy, that is E squared. In terms of momentum, it is P squared C squared plus M0 squared C raised to 4. So you're familiar with this equation too, right? Okay, so now we have two equations for energy. So this is equation 5 and this is equation number 6. Okay, so now we can substitute for kinetic energy in terms of the photon frequency, right? Equation 1, we have an equation here, that is h nu minus h nu dash is equal to kinetic energy. So substituting for kinetic energy and equating 5 and 6 and on solving, we would arrive at another equation for p squared c squared, and that is equal to h squared nu squared plus h squared nu dash squared minus 2 into h nu dash plus twice of m0 c squared into h nu minus h nu dash. So this is equation number 7. So now we have two equations, equation 4 and 7, with the left hand side being p squared c squared. So we can equate both of them, and on expanding and solving, we would arrive at an equation that is 2mc squared into h nu minus h nu dash equals twice of h nu into h nu dash into 1 minus cos phi. This is equation number 8. Now, in order to get the equation in terms of wavelength, we can divide this equation, dividing this equation number 8 by a factor, that is 2h squared c squared, and also using the relation nu is equal to c by lambda, right? This is the relation between frequency and wavelength. Now using these two equations and by this method, we can arrive at the equation for change in frequency for the photons, and which is denoted as delta lambda, which is equal to lambda dash minus lambda, which is equal to h by m0c into 1 minus cos phi. So this is the equation for the Compton shift. Okay, and here this factor h by m0c is called as the Compton wavelength, h by m0c, and the value for this wavelength is 2.42 picometer. So we can see that the Compton shift, that is the change in wavelength, depends on the scattering angle of the photon, that is phi. Now, regarding the experimental demonstration of Compton effect, this figure shows the experimental setup. There is an X-ray source and X-rays are allowed to fall on graphite material, and a detector is placed to measure the scattered wavelength as well as the intensity. Okay, so the intensity and wavelength can be plotted like this. Now this figure shows the primary ray, and after scattering you can see that there is a peak in the wavelength, which means that there is an energy loss. Now, the measurements could be done for different scattering angles, and depending on the scattering angle, the Compton shift would vary, and it is found that greater the scattering angle, greater the Compton shift. Now, it's also possible to measure the maximum change in wavelength. Okay, so for which angle can we expect the maximum wavelength change? Of course, it is for the angle when phi is equal to 180 degree. Okay, so when phi, the angle for the scattering of photons, if it is found to be 180 degree, then the Compton shift would be twice as that of the Compton wavelength. So this is the maximum shift that we can expect in the case of this experiment. Okay, so thank you.